Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. In this video, we are going to discuss the different aspects of modeling and analysis of circular staircase, which is going to be a precursor for the second part, which will be dealing with the design of those things. So with that being said, well, the first things first is, okay, how do those circular staircases look like? Now, please notice that whatever techniques I explained today for a circular staircase work also equally well for circular ramps, which is basically the thing that cars use to access different stories in a car park. I'm talking about circular ramps here. So, okay, well, staircases have different shapes. Most likely, they might be either cantilevered staircases, which means that you can see that each individual stair is carried by a central column, which means that each individual step is being carried separately and standalone as a cantilever from that central column. You could also have continuous staircases, in which case you don't have a central column, but basically the staircases carry each other. And the last part is maybe a staircase that is surrounded by walls on both sides, meaning that each step is carried longitudinally and vertically, and you carried longitudinally and transversally. Of course, you can have combinations of those. For example, you could, for example, have one staircase like this, but a central column carrying the staircase in the center here. Of course, there are multiple combinations for those staircases. I will try to cover the basic ones and leave the combination idea to my dear viewers to investigate themselves. Before I start, I had a small Excel sheet prepared, which helps me understand those circular staircases. So what do we have here? All right, so obviously a staircase is basically there to connect level 1 with level 2. Now, those two levels could be on top of each other, or those could be offsetted. I'll talk about offsetting on top of each other later. If you have two different levels here, you have two levels, for example, difference being 3 meters, it means that you need a staircase that basically connects those two. You could have a circular staircase, or you could have a simple longitudinal staircase. However, our task here is to talk about circular staircases. So I have a difference in level. This is maybe level 1 or first floor, and this is my ground floor. And you want to connect those two things. The first question you will have to ask is to say, how many steps do you want? Because the number of steps, this first variable, the number of steps, basically affects the riser of a step, because a step is comprised, an individual step is comprised of a vertical part and a horizontal part. The vertical part is called the riser, and the horizontal part is called a tread, depending on the country or the region where you are. Both are equally important from an architectural point of view. I know I'm not an architect, but we should know this. Both of them are important because those measure the comfort when you walk on the staircase. Usually the riser should be something between 16 centimeters to 22, and there are outliers where you can, I'm talking centimeters here, and there are outliers where you can break this law. I don't know, it depends on your own thing. And the tread is the horizontal part. I'll talk about this in a moment, but it should be around between, I don't know, like 25 to 30 centimeters. Of course, this depends from country to country. At least those are the things I use when I design. I usually use a riser of 18 centimeters to maximum 20, and a tread of 30 centimeters. Those are my design parameters. But of course, feel free to tell me in the comment what your riser and your tread is. All right. So with that being said, well, the number of steps basically affect the riser, because, for example, if you have 10 steps, then you would have a riser of 30 centimeters, which is huge, by the way. So basically, this gets affected by the number of steps. All right. So what about the tread? When you have a normal staircase, you would have a number of stairs and basically a soffit or a place to stand on. So of course, if you have a number of steps, then the tread is basically determined by you, because it's you who basically decides the spacing of his stairs, and with each spacing, you basically also decide the tread. Of course, this is very ugly looking staircase. I'm actually ashamed of it, so I'll delete it. But before I delete it, You see, you have the option to take the number of steps in any distance. So, for example, you can decide that, hey, I want my step to be 30 centimeters because I have a large stairwell or a small stairwell. In circular steps, this is different. In circular staircases, this is, however, different. Because in circular staircases, you don't have a stairwell that is rectangular, but you have a double circle staircase. And usually it's not a staircase, usually it's in the apartment itself. So you have two circles here. I call this the outer circle and I call this the inner circle. Of course, those have different names. I'm just using very simple names to talk about those things. So if you have an outer circle and an inner circle, and not only this, of course, each circle has its own radius. Not only this, but you can even have an inner circle of 0. And if your inner circle's radius is 0, it means you are now back to the central column constellation, or basically design. So it depends what your inner circle is, what your outer circle is. Also, there are architectural limitations for how large you can make your circles. And the size of the circles matter for a reason I will tell in a moment. Now, before you continue, of course, you can assume that you have a helical, a perfectly helical staircase, meaning that the stairs complete one revolution or 360 degrees while they are going up. I think the picture here shows this. No, most probably no. Like, you can have a staircase that rotates 360, like this one. It rotates 360 before it reaches the next level. However, this is a little bit rare. Usually, our staircases have 270 degrees rotation. Of course, I'm saying usually, but of course it changes from one part of the world to the other. But I will say that I'm assuming now that my staircase is 270 degrees in rotation, meaning if it starts in this position, it will rotate 270 degrees and end in this position perpendicular to your starting position. It's kind of cool, so it looks something like this, something like the lower left one. You start going up, you end going to the left. This is a 270 degree rotation. So I'm going to say that there is a staircase angle. This is one of the design parameters you need to keep an eye on. So total rotation, I will call it. I call it 270 degrees now. I don't know what I called it in the Excel sheet. I just call it total rotation here. So, okay. Now, remember, there is a riser, and I talked about this. It's basically the delta H over number of steps. And then there is the tread, which is the horizontal thing. How do you calculate the tread? This is where things get tricky in a circular staircase. Because if you say that I want 270 degrees, let me give you a design example here. Let's say that we have a staircase where delta H is 3 meters, and you want to use, I don't know, you want to use number of stairs, 20 steps, okay? This means that your riser is 3 divided by 20, which is actually something around 0.15 meters. So a riser is okay in my opinion. Of course, feel free to tell me in the comments what your okay riser is. And let's say you decide that the total rotation is gonna be 270 degrees. Now, with 20 steps, each step will take how much degrees? You basically will define 270 over 20, and you will get 13.5 degrees. This will affect your tread. How? Well, take a look at this. You are basically saying that each step is going to cover a delta theta, a change in angle of 13 degrees, like this. So this slice now is your step. Of course, part of it is air and part of it is step, because, well, there is a stairwell opening here. Of course, if it's 0, then there is no air. So this is your step now, which means your step has a different tread. In the inside, it's smaller than in the outside. And, well, sometimes my personal opinion here is that I use the average tread, or the tread in the middle, as my measuring tool. So you need to find the tread, and the tread here is, basically the calculation is, according to mathematics, arc length equals r multiplied by theta in radians. And this is how you can calculate the tread length. And you need to check this when you design. So I think this is everything I want to talk about for the simple mathematics involved in staircases. So, of course, feel free in the comment section to tell me if you need some more exposition about this. Let's take a look on the little Excel sheet I have done here. So here, it's like a staircase estimator. I said delta H, which is the difference between the two levels. I put the number of steps 15, for example. This is only an example. And I assume that my staircase has a minimum radius of ½ meter and the maximum and a step width of 1.25. What I mean by this is the radial distance, basically, which is this distance in green. This distance in green is the radial distance, which I mean by the step width, because usually the step width should be something around 1 meter, 1.5 meter. You need it to be large enough. Why large enough? Because, like, at least in my opinion, and this is once again opinion, it's not code, my opinion is like 1.25 to 1.5 are bare minimums, because you need the staircase to be large enough to be able to lift stuff upwards. Because, I mean, imagine there is a kitchen on the top floor, on the second floor, and you want to lift a fridge there. Well, obviously, you need some space to do this. Of course, you can have it smaller, but then it becomes a commercial facility where there is only smaller pieces of furniture and pieces of electronics upstairs. So, I don't know, it's up to you. So, okay, you have minimum radius. Of course, you can put it to 0 to make a central staircase, but you have a central column and cantilevered stairs. Those are outputs. The maximum radius is going to be this plus this. The angle per step is, well, the total angle divided by the number of steps. The riser is the division of R divided by number of steps. And the average tread, it's basically arc length, which equals the theta in radians, and you can see that there is a radianization happening here. It's basically the average of those two things, which is the minimum tread and the maximum tread. Minimum tread is internal radius multiplied by the angle multiplied by pi over 180, and the other one is the outer radius. Of course, if we make R internal equal 0, you have 0 internal tread. So take this into account. Currently, I think I'm happy with this. 15 centimeters is a little bit iffy, but you see, this is the problem with circular staircases. I mean, you can increase R and make it 1, and you can have perfectly fine treads here in the minimum, but then the average is kind of big, and you see, it's kind of annoying. So you have to, like, when you have a circular staircase, there is always going to be a place where there is a small tread, another place where there is a big tread. So, okay, I'm going to put here ½ for now and keep it as is. So actually, I'm kind of okay with this. Now to our robot to do this. Now, how can I do that? Well, I'm going to draw me multiple staircases here. I will draw me 3 staircases. The first staircase is a centrally held cantilevered staircase. I'm talking about this thing, about this. And then I will talk about this staircase, which is going to be 2 staircases. The first staircase is going to be a concrete staircase. In that case, you would have a slab or a shell that is basically rotated in a helical way. The second staircase I will be talking about is this steel staircase. In that case, you would have 2 helical beams curving up besides the little steps you have here. I would basically use something like this: a smaller step in the inside, a bigger step in the outside. Of course, feel free to use whatever you want. I'm going to use this, basically. Of course, the torture is going to be how to draw the helical beam, and an even harder task is to be how to manufacture this. But, well, luckily for you, and I'm talking about steel staircases, luckily for you, there are ready-made steel staircases being sold, which are also having inclined beams like this. The final staircase is basically a staircase where you have both longitudinal and transverse supports. I'll talk about this maybe if I have some time. All right, so starting with this, I will go to my view, open my structural axis, and this time I'm accessing the cylindrical structural axis because I want to have cylindrical axis, not Cartesian axis. So, okay, my 0 is basically my 0 position. My inside radius is ½ and my outside radius was, I think it was 1.25, so 1.75. The angle that I'm going to use is, well, 0, and each step has how much? Each step has 18 degrees, so there we go, 18 degrees. I'll apply that. Of course, I need a z-axis here. Now, this is the first story, but I want to add it myself. So 0 and 0.2 is what I want because 0.2 is the first riser. If you hit the apply button, you get this cute little thing that basically tells you to draw the staircase. I'm going to draw multiple staircases, and all of them will have one critical point where you have to pay attention. So the first staircase I will draw is basically a cantilevered staircase, so it will be starting from the center here. This might be a little bit incorrect. I'll talk about the problem I have with this in a moment. Because, truth to be said, even if it is in a central pedestal, you still have the thickness of this thing that supports it. So for me, I will basically, I don't know what I will be doing. The problem is I have foresight, because if you use a point to connect to a column, you will have massive stresses here that are incorrect actually, because you have a surface area to weld to it. It's gonna be tricky. I'll think about this later. Anyway, for now, I'll just use a simplified modeling, and I'll talk about all the nuances later. All right, so what's the thickness of the steel you would be using for this for the staircase? And how do you design this stuff? Now, some of you like to design it as a little bar or a beam. I will just use me a shell, because I talked about the design of shells in my silo video of the steel silo. So please take a look on that video, which is linked above. I'll use a shell. I'll assume a thickness of, I'm assuming steel now. I'll assume a thickness of TH, I don't know, 10 millimeters, for example, or something. Of course, how do I know if it's right or wrong? I talked about this in the previous video. You have to check the von Mises stresses. So I'll add that, use it, and well, I will now do my, what do I want to do? Yeah, I want to do basically this. Now I know what you're thinking. The first step might be redundant, because, I mean, we don't need it. But I will use it anyway. So, and of course, this is a thing that you can easily fix. You can also assume that the first step is actually 20 centimeters on top. A long story, I don't want to talk about this. I will talk about this later. So, let's use a horizontal step, and let's do a steel step now, which is gonna be like this, from 1, 2, no, not rectangle. I don't want a rectangle, contour. 1, 2, 3, 4, oh, this is incorrect. 4, that's still incorrect. Oh yeah, that's correct, okay, fine. 5, all right. Notice that here I'm trying to have my x-axis going as an axis that goes outwardly, and the y-axis is an axis that goes with the rotation. So I need to be careful of how I draw things. So okay, I've drawn my first step. How can I draw my rest of the steps? This is where you need to really pay attention now. So okay, what do I want to do? I want to do this 20 times, and I want it to move in a helical pattern. Now, there is an edit, translate, or copy and move, but that's not what I want, because I want it to rotate. There is also some axis symmetry stuff, but it doesn't work, because this rotates alone, and this moves alone, and this also rotates alone. So is there a way to move and rotate together? The answer is yes, and that's why I love Robot. It's called complex edit, and allow me to explain this. So I select my elements, edit, complex edit, and here both things happen at the same time. You are going to make copies of your thing moving up, and you are also going to make copies of the thing rotating around an axis. So first of all, I will choose translation, because I want this to move 3 meters up. So 3, 0, 0, 3, meaning that the movement is only in x. In z. The second thing is my axis rotation. To do this, I need to give him the axis. The axis is going to be from 0, 0, 0, 0 to 0, 0, 3, basically the height or the central axis of the staircase. The total angle I wanted to rotate is 270. No, wait, that's the individual angle. The individual angle is 18. I don't want to have any scaling effects, because I can make a scaling larger and larger when I leave it without scaling. And the number of repetition is going to be 10. If you hit OK button, magic will happen. So OK. And I think I messed up. Yes, I messed up, because the translation vector should not be 0.0.3, but 0.2. So I messed up. I'm not going to video edit this. I'll leave it. So let's delete this. I'm closing this, selecting again, complex edit. This time it's 0.2, because it's only one step. The axis is 0, 0, 0. And the end is 0, 0, 1, this still works, because the only thing that the program needs is the direction of the axis. The angle is 18, the repetition is 10, and now prepare to see magic. So, okay, and there we go. You have your staircase. And of course, we need still to connect that stuff, but I think it's a job well done. Now, the final thing I want to talk about here is something that will somehow weird you out and allow me to talk about this. So, point 4, point 6, point 8, 1, 1.2, 1.4, 1.6, 1.8. Of course, I could use repetition and distance, but I don't. I'm just trying my luck here. Something will weird you out now. If I hit apply button here, okay, you see, what do you see? Oh, I still have messed up because the number of steps is 15 actually, not 10. I think I messed up, yes. Yeah, this is 180. I should have checked out. That's a mistake. Okay, so how can I fix this mistake? I just realized that, hey, this is not 270, right? That's only 180. So how do I fix this? Well, I have an easy fix for this. I'm also not going to video edit this because I want you to learn. So I will continue my 5 things here. My axis is 0, 0, 0. Let me just do this. 0, 0, 0. End is 0, 0, 1. And I think if I hit OK, it will continue correctly, right? Yeah, now I'm happy. Now I think I'm okay. Now it still will weird you out. It reached 3 meters, you can see from the axis. But you see, there is one redundant step because you always start with the ground. So you can actually delete this because this is the ground level and you don't need a step at the ground level. You don't start at the ground level. This is something that you might have noticed when I was giving you this thing. Never mind, you can basically delete this if you want. I will leave it just because it looks funny. Okay, so I think I have everything right here. The only thing I need now is to apply forces and to apply my supports. So I need to have some sort of helical beam. Now, it's not as easy as you see because the thing here is that there is no helical beam I can put here. The only option I have is to basically give a helical beam that supports it at one point, basically, and rotates. But where is your point, right? Now, luckily for us, this is a non-zero. The problem is if you have a 0 here. So I can put a helical beam that starts from the centers of all those shapes. But however, you would say now, and you are right, by the way, you would say, wait a minute, I call foul here, because the helical beam in the picture is not on the edge of the step, but it's somewhere inside the step. But when I do my approach, the helical beam is going to be on the edge, right? So you'd think, wait a minute, this is not correct. This is cheating. And I give you that point. You are right. I'm cheating now. So how can I uncheat? So now I need to think a little bit. So this is half meters, right? And let's say we want to go inside 0.25, and this is, I think, 1.75, right? So I want to go inside, so I need 0.75, and I need 1.5 because I want to go inside 25 centimeters. So those are my 2 radiuses that I need. I'm still thinking, to be honest, so let's take a look now. I want to go inside, right? So in the radial, I want 0.75 to go 25 centimeters inside, and 1.5 to go 25 centimeters inside. If I hit apply, I can see my 2 circles. Exactly, those are now where my helical beams will connect. All right, so I still need the middle point here, right? So to access this middle point, I am going to, what am I going to do? I don't know, angle 9, I think. I'll apply that. I think we are getting somewhere. So I have a point here and a point here. So geometry, nodes, and let's node that thing. So 1 and 2. See, this is something I should have done before. You see, I should have done those 2 nodes before. Hey, wait a minute, I have a cool idea. And follow me with this. I don't know, I'm gonna think about this on air. I just got a really nice idea while I'm explaining. So I have those 2 nodes. Do I have the ability to drag while I'm complex editing? Because if I have the ability to drag, then I'm golden. Notice, of course, that this is gonna be an approximate method because to do this with the thickness of the beam taken into account, you need a 3-dimensional finite element modeling. Once again, this is real stuff. You're going to use hexagonal elements to do that, at least. So no, I will not be using this. I will just using a simplified version of that, which will look not nice, but structurally speaking, will do this job. All right, so let me think of that. If I take this with 2 nodes and go to edit, complex, I think it will work. And translation is 0, 0.2. Rotation axis beginning is 0, 0, 0. Axis end is 0, 0, 1. My angle is 18 degrees still. And I want 10 steps. But wait, can I drag this? Dragging. Parameters. Hey, there is drag. Will it work? I don't know. Let's click drag and, well, okay. Oh, look at that. Look at this thing. Whoa, man. I feel. Ah, come on. Again, the same mistake. Ah, that's annoying. But I'm still happy. I'm still happy. So complex. I made the mistake of having 10 here. This is some kind of um, embarrassing. Let's select this. Edit, complex, edit. Go here to 0.2 and 0.0.0.0.0.1. 18 degrees, 5 times, with dragging. Not forgetting that. And okay. And this is eye candy. This is amazing. I can tap myself on the shoulder, to be honest. Now, for the really interested here, I made a helical beam. So if you are faced with a helical beam requirement, this is how you do it. But for the real, of course, it's an I-beam. Of course, it's not an I-beam. You should check it out. I just use a placeholder. You can change that. But before this, before you change anything, now some of you might be really annoyed because they would think, hey, wait a minute, you are basically supporting it on the middle point here, but I want to support it here. Well, that's no problem. The only thing you have to do is to put your node here. If you put your node here, you get the support you want. You get the helical beam to be supporting on the edge rather than in the middle. However, looking at this, you can see that those stairs are somehow supported, especially here. You can see it's somehow supported in the center. I don't know. It depends, of course. You have to check out your design yourself, but I've given you the skills. So how would you support this? Now, of course, please notice that this is supported on the ground. This step is redundant. You do not need this. So I will delete it now because you have the ground floor here. And this step may be redundant because you are connecting to the second floor, because you are connecting to the floor level. It depends on your circumstances. I will consider this as redundant because you are connecting with the floor. Now, of course, the floor is itself a structure, and the staircase should be part of a big structure you're modeling, like a big house. Like I have this big house and you have a staircase. But of course, here I'm just going to put me some pins, some good old pins, and end this thing. So here is a pin, here is a pin. Will it be stable? Will pin stabilize it? Let's take a look. Well, torsionally speaking, I don't know. I have some worries. I think this is unstable. I think I should put fixed here because there are some rotations involved. Let's take a look. Of course, we need loads, so I will run the analysis dry run here because next time I'll apply the loads and whatnot. For now, I'm just modeling. So doing this, I'm predicting instabilities. It's not unstable? Huh. That's strange. Okay, now the shell is, in all, for the lack of the better word, it's a nightmare. I don't like it at all. It's kind of annoying, but okay, checking the deflection shape. Yeah, it's exactly as I supposed. Let's take a look. Yeah, exactly as I was expecting it. You have a higher deflection on the outside and the smaller deflection on the inside because the stiffness of the outside beam is smaller than the stiffness of the inside beam. But why is the stiffness of the outside beam smaller than the inside beam? It's smaller because its length is longer. And also, there is more load on the outside because, as you can see, the staircase is larger on the outside than in the inside. So yeah, everything seems to be working as expected. I'm still unhappy with the for the mesh. So let's go to the mesh and select a fine mesh. Okay. Of course, remember this is all under self-weight, so you should exercise caution now. So I said fine, right? Didn't change anything, did it? It didn't change anything. That's strange. Did I select fine? I did, right? Okay, let's go to advanced. Let's force it to use 0.1. Of course, this will now annoy the mesher, like, badly. But well, let it work. Yeah, I think now it's a little bit better. I'm still annoyed about those things. It's like those aspect ratios are not really that bad, but it's not optimized, to be honest. There is more we can do. We should like make now PhD stuff. You should make nodes that go parallel from small to large, similarly to how the shape is, to have a conforming mesh. But never mind. Let's just take a look. Well, I think I think I'm happy with this. So this is the first staircase. A staircase carried by two helical beams. Of course, the helical beams are placeholders. Everything is a placeholder, to be honest. This all needs to be changed. But for now, I'm talking about the analysis only. So, right, we finished our first staircase, right? So since we finished this, and I will upload this, move or copy, I'll move this to the side because, well, mission accomplished. Let's move it 0, 0, 10 meters to the side. So let's move it. I moved it up in the z-axis. I'm gonna leave it just for the fun factor, so let's leave it. The second thing I want to talk about is the cantilever staircase, and the cantilever staircase is connected to a central column. Now, this is gonna be really, really iffy, and I'm totally not a fan of this, to be honest. I'm not a fan of cantilevering your stairs. This works for the smallest of cases, and to be honest, I'm kind of anti this. You need to have at least a support in the middle or somewhere. But still, I mean, okay, let me do this. Of course, some of you could think that this carries tension forces, and it does carry tension forces if it is supported on both edges. However, in this figure, I cannot see any supports. So I think this is carried and not carrying. I think this is carried. Because for something to carry, it must have a huge stiffness and must have adequate supports. If does not have adequate supports, because I don't see it supporting with anything, I see it supporting on the stair, on both sides, because it's not supported well and has low stiffness, I think this is not a carrier, but I think this is a carried entity. So you need to take this into account. Also, you need to take in your loading, you need to take the terrace into account by applying forces on the edges of the staircases. I may or may not do this in the next video because I'm just gonna leave some stuff for you to think about. So I'll just select this. Wait, thickness 75? Did I mess up my thickness? Wait, I think I messed up my thickness, did I? Let me just check. Let's select this. What's your thickness? What's your thickness? Thickness 75. Huh. I messed up my thickness. Well, that's easy. Select everything. So let's fix that. Tick, tick, and done. Now we are done. Now we have our correct thicknesses, right? I think that's the reason why the deflection was large. The deflection was large, yeah, steel. But I didn't talk about this because I thought, well, maybe something wrong. But actually putting 75 millimeter steel plates tends to make loads. So, okay. Anyway, back to our point here. Well, let's select the correct thickness this time, not messing up. I'm gonna make a contour, and this time I'm gonna do this. I don't like this at all, to be honest. I am against this. This is not a recommendation for me. Yeah, and let's run that thing. Of course, notice that column is only a placeholder. I'm expecting massive deflections, to be honest, because, I mean, it is basically a cantilever. Wait, instability. Okay, this is new. Instability of type 3 detected at node 894. Okay, let's take a look at 894. Where is 894? I think I see it now. I think I see the problem. Having a column connected to one point to a shell is a problem in stability because you are unable to protect this against the rotation around X, which makes instability in all kinds of horrible ways. I'm kind of annoyed that my try didn't work, so let's delete it. It pains me to delete stuff, but well, I'm doing this for you. So let's delete this. It's kind of annoying. It doesn't work, actually. I'm totally against that. I should have known. I should have known. So, okay. How do I design this if this doesn't work? First of all, this is, even if you run this, it shouldn't be unstable, right? Yeah, see, this doesn't work. You need to have 2 points for fixation. 1 point is not enough. I will have to take this thickness into account of the central column. So how do I do that? As annoying as it is, I have to admit defeat now and fight another fight. So I delete this, admit my defeat. Actually delete everything here, unfortunately. I delete everything here. And this time I will assume the thickness or the radius of the central column. So if the radius of the central column is 10 centimeters, so 0.1 in the radial, I hit apply, and now I draw the... See, I'm still against those staircases. This is my own opinion. I'm still totally against having cantilevered staircases. But of course, this is my personal opinion. You are not bound to it. You can, of course, feel free to use whatever staircase you want. You are the one who designs it. So 1, 2, 3. I mean, this is having those problems during basically analysis is a warning, a red flag for you to think about. Okay, so now I cannot make one column, So I need to design the column separately. How do I design the column separately? I calculate the summation of all reactions and put it as actions on the column, and this is something I will leave for you. But I want to do the staircase now. So here is two nodes, node here, and those two nodes are fixed. So let's select those and fix them and run the analysis. Of course, the failure attempt from last time for this will not be video edited because I wanted to get to know that, yeah, it's not unstable, it's stable now. I want you to see the wrong way of doing it. So I think now we are doing it the right way. So let's, well, first of all, let's clear the mesh. Yes. And now let's select this. Let's close that. Edit, complex edit. A vector is 0, or 0, 0,2. My axis is 0, 0, 1. Okay, fine. 0, 0, 1 and 0, 0, 2 still works. Angle is 18 degrees, and number of repetition is gonna be 15. This time it will work. So okay, I don't need to drag, by the way. So now I have my staircase. This should work perfectly fine. And note that actually I didn't need to do all of those. Actually, only one stair or one step is enough as a civil engineer. But if you want to really look cool, you can do this. Notice that the fixed support is somehow helical because I have the 0.1 F's offset in the radius. If you run the analysis now, everything should be working out and everything should be checking out. Of course, you don't have only one separate structure. You have tons of separate structures. This is okay, so no problem. And well, it should work. Of course, here the deflection, if you open deflection, the deflection is off the charts, 174 millimeters. That's a lot. 10 centimeters? That's really, 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 really a lot. I will think of, oh yeah, of course, yeah. Because it's cantilevered, so my 10 millimeter thickness will not be enough. I mean, when it was supported by two beams, 10 millimeter thickness might be okay-ish, but having a cantilever, the 10 millimeter thickness will never be okay, so it must be fixed. But okay, at least mission accomplished. We have analyzed and successfully modeled this staircase. So okay, let's take it, edit, and throw it away. So edit, move or copy. Let's move it 10 meters to the x-axis this time, not the y or z. So we throw this away, and now we have another staircase on the right side. Going on with this, we now make a concrete circular staircase. And what I will explain now works for both concrete staircases and concrete ramps for cars. Now, for concrete, it's a little bit different because in concrete, you do not have those steel elements where each one is basically one element by itself. You have one monolithically cast staircase. Allow me to show you this. Yeah, see, this is how it looks like. And the formwork for that thing is a nightmare to do. This is really, really hard for us to do as civil engineers. Let me copy the image here because I want to talk a little bit about the analysis of that thing. How do we model it? You see, we have an approximate modeling here when we do this. We model the thickness of this slab as being one continuously cast, monolithically cast slab, this one. This thickness is what we model. And the risers and treads, this is, by the way, called the riser, and this is the tread. They are just added as weight because this is the effective thickness that resists everything. I know it's more, but this is the approximation I was using. I don't know if you use it. Tell me in the comments if you use this. So this is the thickness. It's actually a somehow helical concrete slab that is rotating with the staircase, which is really, really a challenge to model. But luckily for us, we have Autodesk Robot, and you have me. So let me explain this to you. All right, so notice that I don't care about the riser and tread. I'm going to draw me an inclined slab. So allow me to tell you what I will be drawing in red. So the red line here, this is what I will be drawing, this piece. This is my element that consists the staircase, and I will be drawing elements element by element. So how do I do that? It's still not as clean as I wanted, but it's the best I can do, truth to be said. It's not as clean as I want. I told you the problems here. It looks nice, but look, I'm always frank to my dear subscribers. So it looks nice, But there are some nuances in the modeling, to be honest. So, okay, I'm just going to fix it on both sides. Well, deflection. Yes, it does work. Hey, I'm still annoyed by this. Look, the Mesha is really fighting to his death here because you have so badly shaped elements. But it still worked. So I'm kind of annoyed because, I mean, I don't lie to you. This is a little bit, whenever I see this in a mesh, whenever I see this conglomeration of nodes in a mesh, I immediately get wary and know that there is something wrong here. Anyway, first of all, before I finish, let me check something because I don't want to admit defeat easily. So I just select 10 thickness steel and select this and basically apply to it the thickness 10 steel. Yes. Just for a placeholder now. And I will take this and move it. Edit, edit, move or copy. And move it, I don't know, -10 in X, 0 in Y, 0 in Z. I'll move that, so move. Let me try the curved shape again. Maybe a robot is able to mesh it, maybe. This would be a real surprise. I never have seen a software do this before, so I am not expecting much. But, well, let's just try again. I want to give robot one final shot. Yeah, see, when you model, you have to have a little bit of nerves, otherwise you will give up immediately. So let's get back to this. So this has a problem that it is not a plate. But will robot be able to mesh it? That's a good question. So let's fix it here and let's try run it. So run. Let's just check if it will work or not. Will it work? Now it meshed. Oh, wow. Wait, wait, wait. Oh my God. This is genius. This is amazing. Robot, okay, it's official. Robot is bloody amazing. Oh my God, look at this. Look at the beauty. I'm sorry, I seem like a fanboy right now, but I know what I'm talking about. Meshing this is a nightmare. It does calculate, it does scale. So this should be impossible to mesh. Yet robots seem to have meshed using triangles, obviously, to have more accuracy. I tried doing a rudimentary triangle thing here, but robot, of course, is like ways ahead of me. So let me try. This would be amazing if it works. So let's select this. Now, first of all, no support, because otherwise it will take the support with it. So let's remove the support. This is a long video, by the way. Geometry, edit, edit, complex edit, 0, 0.2, and 0, 0, 0, wait, 0, 0, 0. Okay, and the axis is 0, 0, 0, 0, 0, 1, and the angle is 18. The number of times are 15. And fingers crossed. Okay, so we have it. This is not everything because the mesher is still the final culprit. Will it mesh? So, one final thing I forgot to mention is that the slope needs to be taken into account for circular or cylindrical stairs. But well, the riser and tread will take care of it. So fixed and fixed. And this is the final boss. Run. Let's hope it works. You see, the finite element calculator is really taking a lot of time. Ho, 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 ho. Look at this beauty. Look at this mouth-watering beauty. This is amazing. This is next level meshing. This is amazing. I have no words. I'm lost for words. I'm sorry, this is beautiful. Ladies and gentlemen, I don't know if I cannot I cannot overstate this. This is amazing. This is okay. I mean, this is my little rudimentary try, but this try stems out of my understanding of plates. But this, I never expected robots to be able to do this. I never expected it. I had zero expectations, and now I'm speechless. I hope that you learned something new in this video. I will be uploading this usually on the YouTube channel for you to see. Before I finish this video, I want to wish you a happy new year and we will meet in 2023. So I hope this video was beneficial for you and that you learned something about in it. Of course, if you have learned something and you kind of like it, then of course, please like, share, subscribe, and comment. especially subscribing because it helps increase the reach of my channel. This is the Civil Engineering Essentials channel, and we will catch you in 2023.